Welcome to another edition of 462, Experimental Analysis of Behavior. And we're going to discuss today a topic near and dear to my heart, and that is disequilibrium models. So let's see if I can pull up my window and share with you disequilibrium models, which I love because they're my research area. All right, let's see what we can do. So a disequilibrium approach uses the idea that we want our bodies in equilibrium, and we will work to get our bodies back to equilibrium when we're in a state of disequilibrium. But let's start at the very beginning of the story for how these models kind of came about. So we have to kind of go back to, in talking in applied analysis of behavior, what is the goal of behavior analysis? And it's certainly to clarify and control human behavior by use of reinforcement contingencies. And over the years, since Skinner was around, many techniques have been developed. And of course, behavior analysis is used in a wide variety of settings, from hospitals and clinics to schools to business and industry, in animal training at zoos and animal shelters, and everywhere else. And one of the problems with this is specifying ahead of times what will be a reinforcer, what's going to work. And given the definition that Skinner has, there's no a priori way of determining what a reinforcer is. A reinforcer is anything that increases behavior. So how do you know what increases behavior? Well, you apply it to the behavior, measure to see if behavior increased, the baseline behavior increased, and then determine it's a reinforcer. And this makes for problems in applied settings and even laboratory research to some degree. Because if I'm using reinforcement to improve a child's behavior in an applied setting, or even in the research area where I'm assuming that this is a reinforcer and I'm trying to manipulate a particular behavior, I have to kind of check it out first and make sure it's a reinforcer before I can use it. And the way that it's typically done in applied settings as well as research settings is something called a reinforcer assessment. So we give the child or the animal a variety of foods or toys or things to manipulate, and we see which they spend the most time with and which they spend the least time with. And from that, we can kind of assume what they're most likely to interact with and what they're least likely to interact with, and we can rank order them and therefore have a reinforcer assessment. The problem with this is they're very time consuming, and they're not very accurate in that the child's preference or the animal's preference may change over time, and so you have to redo them every now and again. And the question is, how long is now and again to determine whether or not the reinforcer assessment remains accurate? So we can also probably agree that there are three practical requirements that an a priori assessment should satisfy. And so identification of the response circumstances should involve a small number of simple, non-intrusive procedures. So if I'm going to look to see how a reinforcer affects responding, I want to be able to do this very simply and hopefully non-intrusively. And my reinforcer assessment should be widely applicable. It should require no special apparatus, so I don't have to bring in all sorts of sensory toys. I don't have to go out and purchase a whole bunch of different kinds of foods that I'm only going to use a little bit of for the reinforcer assessment. And you can also argue that it shouldn't be introducing novel or disruptive stimuli. So I shouldn't be introducing, candy to the children or, in a sense, treats to the animals, because that's non-nutritious and is also novel and not typical species behavior. At the same time, we want our reinforcer assessments to be accurate and complete. Well, that makes sense. If I'm going to use them, they should be accurate, and they should be relatively complete in that they maintain for the setting circumstances in which the organism is going to work. And the result of these reinforcer assessments should be a reinforcer assessment that's adaptable to a variety of situations rather than limited to a small number of stimuli, responses, or settings. So hopefully I come up with a reinforcer assessment that goes across settings as well as within a setting, or at least related settings. So the traditional approach to this emerges out of the equipotentiality principle. And this is the conceptual analysis in the article by Paul Meehl that we read from 1950. And the assumption is that the simplest method for figuring out what works, what is a reinforcer, is using what circumstances have worked in the past. And so Meal's approach is if it worked in one setting, it should work in others. If it worked yesterday, it should work today. So use what the organism had as a reinforcer successfully in previous settings and bring that one into the new setting. And so a reinforcer should be reinforcement across situations or transsituational. And there are three important assumptions about reinforcing stimuli and their setting conditions according to this transsituational approach. First is that reinforcers and punishers form unique, independent sets of transsituationally effective stimuli. So these reinforcers and therefore punishers are effective across situations, and they assume for the lifetime of the organism. The essential function of the contingency is simply to produce time pairings or temporally proximate pairings between the response and the reinforcer. And a deprivation schedule is required. I have to use long-term denial of access to the reinforcer in order to increase the desire for that reinforcer, and this becomes a critical setting condition. I can't have giving you Oreos for, say, 6 weeks before so that when you see an Oreo, you know, want an Oreo. And this was done to get around the satiety issue, that I'd had too many of those already. Well, we'll just deprive you of it and then you'll want it. The problem is none of this holds water. Reinforcers and punishers are not mutually exclusive or transsituational. In fact, in Premack's reading that we read, we know that drinking and wheel running can reinforce one another. It all depends on how you set it. Applied settings observe this all the time. A reinforcer is not a reinforcer for everyone. Not everyone likes chocolate, and there are some people who find electric shock reinforcing. We also know that what was a reinforcer when you were 4 might not be a reinforcer when you're 24. So that again, reinforcers are not necessarily things. They can actually be activities, and they're not mutually exclusive or transsituational. We also know that temporal contiguity is not sufficient to produce reinforcement. Just because 2 events occur next to each other doesn't make them a reinforcer or a punisher. What makes them is a contingency between a response and the next event. So it has to be a contingency. And in fact, Premack showed that you could have wheel running and drinking right next to each other. The animal could engage in either, and they weren't reinforcing until he set up a contingency where you had to do one to get to another. So it appears that the contingency is key and not the time or temporal contiguity. And Premack didn't specifically address this, but I'll tell you that long-term deprivation is not necessary nor sufficient, that short-term deprivation can work. And Premack indeed himself used short-term deprivation rather than the long-term deprivation, that you only had to be deprived of the item very briefly in order for it to work. And in our final model, we'll see that we don't even have to do much more than a momentary deprivation. Now, the other problems with this transsituational situation is that it's still the most used technique. Okay? People assume that if it was a reinforcer yesterday, it must be a reinforcer today. And if you had Barney stickers as your reinforcer when you were in 2nd grade, they're still effective today. The other thing is the assessment techniques to do these reinforcer assessment procedures are very intrusive and can often take days away from any kind of intervention, which if you're working with a small child who time is of the essence, this can be very problematic, especially because these reinforcer assessments are not very effective. And the idea that a reinforcer is a reinforcer across children, so all children like chocolate, therefore that's what we're going to use, is not very effective at all. Reinforcers change across individuals, across settings, and across time. This model doesn't really account for satiation effects other than to say I have to give you long-term deprivation. But how long can I use a reinforcer before I need to, again, invoke long-term deprivation? So if I'm using candy, how soon is it that satiation sets in so that I have to then stop that reinforcer, which flies in the very face of a reinforcer is a reinforcer is a reinforcer. So this procedure lacks flexibility, it lacks accuracy, and then we have a whole nother issue of ethical questions when using food, when introducing novel things that disrupt the normal behavior of the organism, and in the use of certain punishments. because we know things like hitting or electric shock at a high enough charge certainly is a punisher across settings and species, but it also can kill the organism. Well, dead organisms don't behave. And again, many parents will complain about the use of food items in school or giving children toys and more items that they don't really need. And in all honesty, lose their value very, very quickly. So even though the transsituational approach is still the most often approach used, it's used inaccurately, and we need to better train our behaviorists. So Premack in 1959 and 1965 came along and developed the probability differential hypothesis, or Grandma's law. And this probability differential model says a schedule in which a higher probability response is contingent upon a lower probability response will result in reinforcement of the lower probability response. We can say this very easily. If you eat your peas, which is a low probability behavior, then you can have chocolate pudding, which is a high probability behavior. So you can't do something you like to do a lot until you do something you don't like to do very much at all. And so we've simply set that contingency, and we know that that works. And again, notice we're using peas and pudding, but it's not looking at the peas and looking at the pudding. It's engaging in them so that pea eating becomes an activity. Chocolate pudding eating becomes an activity rather than seeing these items as things. And again, there's an important change in the concept of reinforcement. Reinforcement is now access to a response rather than reinforcement being a thing. The probability of a response is determined by the probability of a response in free baseline. So we simply give children the chance to play with toys, and we look to see how much they do toy playing versus how much time they spend maybe sitting at their desk doing math problems. And what we'll know is that there are many children who spend more time playing toys and doing math, but there are some children who spend more time doing math than playing with toys. So for toy playing children, we can say you must do your math before you get to play with toys. And for children who have low frequencies of toy playing, but high frequencies of math behavior, we can say, I'm sorry, you need to do your math or before you can play with toys. Or you need to play with toys, let me get this right. You need to play with toys and before you can do math problems. So for most children, no toys until math. For other children, no math until toy playing. And again, we can work with both children, and we would assume that we want children who can play with toys. We also want children who can engage in math. So we might want to increase the probability of both behaviors, but for different rates and for different children. There's still some problems, however. Premack was incomplete and unclear about a couple of things. First, he failed to specify the conceptual rules for setting the values of a contingency. Do I pair 1 pea per 1 chocolate bite? Do I pair 5 or 1? What is it? So he was relatively unclear about how to do that. And what most people do is simply eyeball it and use some common sense. You know, how many peas do you want the child to eat? How many bites of chocolate pudding is in a typical, dessert bowl? And we'll make that our contingency. But that's not really scientific. That's kind of on the fly in the real world. He was also unclear about the role of the reduction in contingent responding relative to baseline that often accompanies an increase in instrumental responding. Say what? Well, one of the problems when you constrain the both free baseline behavior, so you constrain both the pea eating and the chocolate eating into a contingency, is while rates of pea eating increase, the access to chocolate pudding actually decreases. Typically, there's kind of this middle ground where children will say, okay, I'll increase my peas this much to get this much chocolate pudding, but I'm not willing to start eating a whole bowl of peas to get more chocolate pudding. And so there's some kind of middle ground, and he didn't really specify that. Our next model will. He was also unclear about the role of long-term deprivation. He tended to use short-term deprivation, so 30 to 60 minutes before he interacted with a child or a rat or a monkey. If it was a food reinforcer, maybe days between trials, a day or so between trials for his monkeys who were doing various plunger pulling and door sliding. So he was using some short-term deprivation rather than long-term deprivation, most certainly, but he wasn't clear about why he was doing that or why the long-term deprivation was unnecessary. And again, he just got interested in other things before he went on and never really finished his model. Other people came along and worked on that model for him. Now, applications again, this is also probably a widely used behavioral technique, if not the most widely. It's starting to replace that transsituational as more word gets out. And in fact, I laugh in the dog world, pre-mac has now become a verb. Oh, I'm going to pre-mac today. Oh, you're going to use pre-mac's model? No, I'm going to pre-mac, which tells me they don't really know what it is or it's theoretical, but it doesn't matter if they're using it correctly. And again, the procedures are relatively clear and non-disruptive. You have to do 10 math problems before you can go to recess. And the longer you take to do your math problems, there's decreasing time at recess. So if you're not recess is at noon and you still haven't finished your math, and maybe recess only goes till 12:30, for every minute you take longer, you're losing a minute of recess. So now the contingency is the faster I get done, the more recess I get. So there's some ways that we can introduce that, but those are natural behaviors. I haven't introduced candy. I haven't introduced anything that is really invasive. It's certainly more accurate than the transsituational method, and it allows for a far wider choice of reinforcers and punishers because they're no longer tied to being a thing. Reading, rather than a number of books, reading a book might be very reinforcing. It also might be the instrumental behavior that we're trying to increase. Right? Playing outside. Well, that's not a thing. You can give children things to play with, but one ball is reinforcing if I get to play with it for the afternoon. So again, it's far wider. It really opens up what is and is not a reinforcer and even a punisher. Timeout is a form of punishment by definition. What is timeout? It's timeout from the opportunity to earn reinforcers. But even in the applied arena, there are some issues. How do you measure probabilities? And a discrete response, like I want to get so many cards, is difficult to measure. And I laughed because a good example of that is the Pokemon game, where you have to get so many of the Pokemons. I hope I'm saying that right because I don't play the game. But how do you measure? Well, you need to earn, if you do your math, you can earn 4 Pokemons because it depends on the distribution of those things that you can pick up and where you're at. So if you're on the quad, there might be a variety. If you're out by my house in the middle of nowhere, there's really very little opportunity. There's much fewer. So that discrete number is hard to measure. How many responses? Again, that gets back to how many peas versus how many bites of chocolate pudding. Duration, by the same token, is not always a good measure because maybe I eat my chocolate pudding really fast, but it takes me an hour to eat my peas. Well, then by definition, pea eating should reinforce chocolate pudding because I spend less time eating chocolate pudding while I'm taking more time to eat my peas. So it's, again, people eyeball it and use it, but theoretically, that even it's not a good explanatory device. And if we don't have a model that can account for that, it's hard to direct people on how to use it. Right? And again, we always have to worry about higher versus lower probability responses. Well, I can show you how you can use equal probability responses, or even sometimes a lower probability response can reinforce a higher probability response. I'll tell you about that next. And it can still be time consuming to measure baselines because we have to look and see how long does a child spend doing a variety of activities. And of course, a teacher can eyeball this. Does a child spend more time out at recess if they're given a chance, or do they spend more time in math? Do they ask to stay in at recess and do academic work? You probably have a better idea that they like academic work better than recess, and so on. But again, we want to make this procedure as streamlined as possible and be able to theoretically account for it. And the pre-mac model is almost there, but just not quite. So let's go to model number 3, the response deprivation and disequilibrium approach. And again, the assumption is that reinforcement results from the adaptation of motivational processes which underlie free baseline responding to the performance constraints imposed by a contingency schedule. Huh? Well, your reinforcement effects, those effects, are an adaptation from what you want. So if we use our motivational approaches, you have a free baseline that tells you how you're going to behave. And we don't like our normal pattern of behavior disrupted. And the basic idea is if I disrupt your normal pattern of behavior, you will work to get back to your normal behavior. So constraining a behavior, which is when we interrupt it and don't allow it to occur, will and make you do something else in order to get that behavior back, can be a reinforcer condition. Taking a behavior away in order to get you to do something can also be a reinforcing condition. So I can constrict your everyday behavior, your normal patterns of behavior, and restrict it, and then put those free behaviors into a contingency schedule, and it will increase or decrease responding. Let me give you a couple examples here. What we're really looking at is a molar equilibrium theory. So the idea is that all behavior is purposeful, and all behavior occurs in kind of a pattern. We know we have diurnal rhythms, we have nocturnal rhythms. We tend to sleep about as much. And even if you look at things like coming in the door after coming home from the lab or coming home from class, you find that you come in the door and you either take your shoes off first or your coat off first. Where you put your keys is fairly consistent, so that your pattern of coming in the door behaviors is quite consistent on a day-to-day basis. Well, what happens if we interrupt this flow and pattern of behavior? Well, you'll feel upset. And if you've ever been in a kind of group living situation where you know about how much time you have to take a shower and get out of the house, there's nothing more irritating than somebody getting in the bathroom before you and disrupting your schedule. So now your whole schedule for getting out of the house is off, and you have to kind of make do and figure out around it, and you feel very disgruntled and upset. Well, that's what we're going to use. We're going to use that motivational process of feeling uncomfortable to have you work to get back to your free baseline of responding, your normal pattern of responding. And we're going to do this, and we're going to make you uncomfortable by imposing a contingency schedule on your behavior. So in this case, behavior, your hierarchy of reinforcement values are not a stable baseline. We know that what you want at any given moment depends on what you're doing and what just happened and what's about to happen. But we can use that moment of behavior to kind of figure out where you are in your pattern of behavior and disrupt it somehow. So if you're watching TV, I stand in front of the TV and ask you to solve a simple math problem. And if I say, hey, what's 2 plus 2? You'll probably say 4 just to get me to move. That sounds silly, but we can use that with small kids. Or we can have timeouts in their computer program where they have to answer a response in order to get back to their program, kind of like the commercials where you have to watch it for so long before you're allowed to hit the skip button. Again, you're still getting exposure to that commercial. And what are you doing? You know that you have to sit through 4 seconds of that commercial in order to get back to your regularly scheduled program. And so we can do this, and we're going to call the reinforcement procedures that are going to use a response deficit. So I'm going to increase responding by invoking a response deficit. I'm going to decrease responding by using a response excess method. Okay? So it sounds funny because reinforcement should be excess. Now, I'm manipulating the contingent behavior. I'm manipulating the reward behavior. So I'm going to say I'm getting a deficit in chocolate pudding eating if you don't eat enough peas, and I'm going to give you an excess of spankings if you keep hitting your sister. Okay? So we'll figure out how this works, and you'll see there's actually quite a logical model. So in order to invoke a response deficit, I have to impose the contingency I over C, instrumental divided by contingent response. And it has to be a greater number than my baseline instrumental to contingent responses. So by definition, if the individual maintains instrumental responding at the baseline level, they would engage in less baseline levels of contingent responding under the contingency. So if my baseline pea eating is 1 and my baseline chocolate pudding is 10, okay, so 1 pea for every 10 bites of chocolate pudding, I can simply invoke, so that's 1 over 10, right? 1 pea divided by 10 chocolate puddings. Well, if I change a contingency to 2 peas for every 1 spoon of chocolate pudding, in order to maintain your baseline rate of chocolate pudding eating, which is 10 spoonfuls, I have to eat 20 peas. So now I have to, if I continue my baseline level of peas, how much chocolate pudding would I get? A half spoonful or no spoonfuls. Instead, with my contingency, I have to increase to 20 peas to maintain 10 spoonfuls. And that's a 20-fold change in pea eating to maintain my chocolate pudding eating. So will you go ahead and eat 20 peas? Maybe, maybe not. It depends on how near and dear chocolate pudding is to you and how icky pea eating is. What we'll see is some approach of the pea eating to maintain some approach of the chocolate pudding eating. And I'll show you how you can determine this in a moment. Now, a response excess is the opposite. Here the I over C has to be less than the OI over OC. So the instrumental consequence ratio has to be less than the baseline instrumental to baseline contingent response. All right. So if the individual maintains instrumental responding at baseline level, they would engage in too much of the baseline level of contingent responding. So let's say I hit my sister once per hour, and my baseline rate of engaging in spankings is 0. The contingency is going to change this. Now, I'm simply, because 1 over, 0, pretend it's not an undefinable fraction, basically to be infinity, I can hit my sister as much as I want and never get any kind of consequence of spanking here. Well, now I'm going to make it a 1-to-1. 1 spanking for each episode, right? So now this is 1-to-1, where here this was infinity. Well, now every time I hit my sister, I get tremendous more spankings than I ever wanted because my baseline was 0. And I'm likely to reduce the number of times I hit my sister to 0 to maintain 0 spankings. Yeah, depending on what my sister does, maybe every now and again I'm willing to take a spanking to get her a good whack when she really irritates me. But in general, I'm going to greatly reduce the number of times I hit my sister to avoid any increase in spanking. Okay, why is this weird way of looking at things an improvement? Well, number one, it specifies the rules for setting the terms of the schedule. I have to be bigger or I have to be smaller, right? So I is your instrumental, C is your contingent. So your ratio of instrumental to contingent responses, how many peas to get how many puddings, has to be greater than the baseline rate of pea eating to chocolate pudding eating for reinforcement effects, and has to be smaller for punishment effects. How big or how small? We'll get to that in just a second. But I can specify the terms of the condition. There are also no limitations on units for measuring the baseline behaviors as long as I keep the same in contingency setting as the original ratio. So I can have numbers of peas and minutes of TV. Well, those are totally different. One is time-based, one is physical number of an object. That's okay. If I want 30 minutes of TV, then I have to eat so many peas. It also sets no restrictions on what can be a reinforcer or a punisher. So now, for the weird child who loves peas and hates chocolate pudding, they can have to eat chocolate pudding to get access to peas. And if you think about it, and Bill Timberlake's one of his best examples was having to go to the bathroom. You probably go to the bathroom far more or far less in terms of minutes than you do in the amount of time you read. But there are times when I can make you read a paragraph to get to the bathroom. So you have to go to the bathroom and you have to go to the bathroom, and I'm blocking the door. I will not let you in the bathroom. And I say, you must read this paragraph before I'll let you in the door. You will read that paragraph, even though reading is already a very frequent behavior. You read some more to get access to that low probability behavior of going to the bathroom because there's some other kind of biological motivation going on there. You don't want to wet your pants. And so suddenly you'll do something that you do frequently, but you'll do more of to get access to a low probability behavior. And again, that's kind of a silly example, but that is within the model, so we can account for some of those kinds of silly examples. And that's really important. So again, lower probabilities can reinforce higher probabilities as long as the setting conditions are met. I don't need a long-term denial. Your mother does this to you all the time without long-term denial. You reach for the potatoes across the table, and she grabs the potatoes, moves them farther away, and says, "What do you say?" And you look at her with a briefly blank stare, and you go, "Oh, please, may I have the potatoes?" And then she passes them to you. Right? You didn't have to be deprived of potatoes for a long time. You simply had to be deprived at that moment, so that as you reach for the potatoes, she took away access contingent upon you saying please. And this is important. I can immediately disrupt an ongoing behavior and get it. If you're walking down the street and I block you, you want to continue walking down the street. And if I say, "What's 2 plus 4?" you'll answer 4 to get me to move so you can continue walking down the street. I didn't have to deprive you of walking. I simply had to block your ongoing behavior. And certainly long-term denial is a special case of this disruption, but it's not necessary. So how can we use this? Well, there are a variety of procedures that are most specific to this that are relatively non-disruptive, more accurate, and allow incredible flexibility. And two of the best examples were done by Ed Konarski. He's actually an IO psychologist, but he was working with children at the time, and he had grade school kids. And he looked at how often they would color. So say, okay, you can color these pictures. And again, they're young children, third and fourth grade, and how much time they spent working on arithmetic problems. Well, obviously, most kids would rather color than work math problems. So he said, fine, you can color as much as you want. We're not going to do math anymore. You can color all through math every day. So math time came in their daily routine of class. And he said, nope, we're not doing math today. We're just going to continue coloring. Well, that was great for a couple of days. But now the kids were beginning to get sated. They were getting sick of coloring. And math was kind of in their daily schedule, and they'd always done math before. They actually began to miss math. And so he made a contingency. If you color for 45 minutes today, then you can earn your math back. And the children would do it. And again, he did this with what he called retarded children. And there's an article back there. We call them developmentally disabled or cognitively impaired kids today. They were what they called educationally mentally handicapped back then, or low to moderate functioning kids. And again, he had arithmetic problems and writing, both academic tasks, right? And he took math away, and they had to write longer. Well, that sounded great at first, but they got tired of writing and asked for math back. So he said, fine, if you're working on spelling and writing, you have to get 100% in your spelling test, and you can earn math back. How do you earn your math back? You earn it by getting 100% in your spelling test. But notice what the reward for getting 100% on the spelling test is. It's getting math, the stuff they didn't like at first. And so he made them earn one for the other, and he could flip-flop it back and forth. And again, we can have children earn something that they normally didn't like simply by briefly taking something you didn't like away. And if it's part of your daily schedule, if it's part of your ongoing normal activity, you'll miss it and you'll earn to get it back. We've induced this disequilibrium. And again, we use this in something called incidental teaching, which is what your mother is doing when she takes away the potatoes. We show something to a child, I have a toy, and maybe I'm working on the concept of blue. And so I put lots of blue objects out. And the child reaches for the blue truck. And I'm fast, I beat him to the blue truck, and I play with the blue truck, and I'm moving it along. And he's reaching for the blue truck, and I say, oh, do you want this? Well, of course he wants it. He just reached for it. And I say, you want the blue truck? Oh, can you tell me you want the blue truck? Use your words. And the child says, blue truck. Great, he got the blue truck. Why? Because he asked for it with his words. I might have them name the color. I might have 3 blue trucks and he has to count them to get access to them. I can use it in a variety of ways. But how do I know what the child wants? Because he reached for it and I took it away. So I'm actually imposing a brief disequilibrium, and that I took something you wanted away from you in order to get you to make a contingent response. Behavior contracting does this. And again, we make a contract with your behavior. You will, remember to make your bed 5 days this week. And if you do, you get to go see a movie. So now I've literally written out the constraints. What do you have to do, and what do you do if you get it, if you actually do that? And we know that behavioral contracting works very, very well with higher functioning people, with adults in particular. It makes them be aware of their behavior, and it allows them to continue on and arrange their daily schedule, knowing what the contract is and what the consequences are going to be. We use this with the good behavior game. The good behavior game we play, there's always that one kid who ruins everything, right? He's always the bad kid and he gets everybody else in trouble. Well, what happens then is that people begin to notice the bad kid when he's bad, and the child is actually only getting attention when he misbehaves. So how can we change this? We can reward children for attending to that child when he's good, and you make a game out of it. So you might form 2 teams in the class, divide the class in half, and whichever half of the class can find more things that Johnny does good in a given week, they get a special prize. Maybe they get 10 minutes extra of recess with Johnny. And the idea is, rather than tattling on Johnny and telling the teacher what Johnny does bad all the time, now the children are reinforced for finding out what Johnny does good. Well, now the way that Johnny gets attention is by engaging in more behavior. And so Johnny's getting reinforced and the children are getting reinforced for positive behavior together. A punishment version of this is something called overcorrection. So I didn't want to do something, and I threw my papers on the floor because I didn't want to do math. Well, I've got to have a punishment for doing that. If you throw your paper on the floor, first there's restitution. I have to pick up the paper, straighten out my paper in my work area, and if I've ripped up my paper, I have to go and get a new paper and bring it back to my desk. And then, since we all know that papers don't belong on floors, I have to practice getting the paper off the floor and putting it on my desk. So I might be made to walk over to the teacher's desk with my paper, pretend I'm taking it out of the box and bring it back to my desk, sitting down and putting my name on that paper 10 different times. I'm practicing the appropriate behavior over and over and over again. And it's punishment. It's no fun. When I was the school principal many, many years ago in a different life, I used to do this for children running in the hall. When I caught a kid running in the hall, I'd say, "Oh, you're showing me that you don't know what walking feet are. How do we move in the hallway? We walk. That's right. You need to go back to the end of the hall and show me walking feet." And the child would have to go back to the end of the hall and walk to me 10 times. Well, if they were running on their way to recess, they just lost 5 minutes of recess for showing me and practicing good walking feet. It's no fun at all. But it's a very effective punishment, right? You don't put your clothes in the laundry basket. Oh, you must not know how? I'm going to dump the laundry basket and make you fill it up 10 different times to show me that you know how to do it. And again, what I'm doing is you're practicing the appropriate behavior, but I'm also over practicing that behavior. I'm making you do too much of it. And what the threat is if you don't put your clothes in the hamper the first time, you're going to have to do it 10 times instead. And that would be more punishing. You'd have to engage in more hamper behavior than you ever wanted to do. And so you'll avoid doing that, or at least avoid getting caught. My favorite one of these kinds of contingencies is when my son didn't want to take a bath when he was young, and he wouldn't take a bath and wouldn't take a bath and wouldn't take a bath. So I took baths away from him. Everybody else in the house was allowed to take a bath or a shower. That's my new rule. I wrote up a sign. Everybody else can take a shower. Mac cannot take a shower or a bath. Well, within 3 minutes, he was screaming, "That's not fair. That's not fair. Everybody else gets to. I want to too." So I said, "Fine. If you want to take a bath, you have to earn a bath. You need to go and pick up 10 toys, and then I'll let you take a bath. So I both got toy behavior increased, toy put away behavior increased, but I simply got him to want to take a bath by taking baths away from him. Parents have used this model for years. They just didn't know the theoretical reason why it worked. They call it reverse psychology. Well, it is reverse. You're reversing the contingency to disrupt their equilibrium. And so by putting them in that state of disequilibrium, they'll work back or reverse it to get back to equilibrium. It's so much fun. And how do we know how much to do this? Well, there is a minimum bliss point model, which comes out of behavioral economics, which we'll also get to. We can import here because this model is actually a form of behavioral economics. And what it says is there's a bitonic relationship between the rate of reinforcement imposed by a schedule and the strength of the reinforcement effect. The response rate first increases, then decreases as the reinforcer rate increases. So you get a inverted U-shaped function. When the schedule provides a very high rate of reinforcement, it disrupts disequilibrium only slightly. There's little change to the instrumental responding. But when the schedule provides a very low rate of reinforcement, you're not getting any reinforcement at all, you also get very little reinforcement effect. So if I don't get any reinforcers, I don't do the behavior. But if I get too many reinforcers, that actually goes the other way and it begins to sate me. And so I stop being the behavior. So extreme rates of reinforcement should be less effective than moderate rates. And indeed, that's true. And we can determine how much on, and typically we use a fixed ratio schedule, and we'll use this as our example. We can determine how much I need to disrupt according to this minimum bliss point model, where R, the response rate produced by the ratio schedule, is equal to the predicted rate of reinforcement, or the predicted rate of reinforcement is going to equal the OI, or the rate of unconstrained instrumental response, plus K times OC, or the contingent response in baseline, divided by K squared plus 1, where K is the number of units of reinforcement or response, and is typically the inverse of the FR requirement. Okay? Just believe me, this is true. So typically, we demonstrate it like this. Well, here's our bliss point. Here's where our predicted maximal amount of reinforcement would be. So here's basically free baseline. And then if I impose this schedule where you have to do this much, say 25 minutes of math problems, gives you this many minutes of recess. So now I've imposed a schedule. But if I impose 40 minutes of math problems, then taking away from your bliss point, I only get this much. And what we're happening is we're dropping the perpendicular at each curve, at each, this would be our schedule constraint. I take from my bliss point the perpendicular to the curve, and I can predict this. Now this is hard because it's graphed funny. Let me do it this way. And this would be typically how we'd plot minutes of recess and then how much minutes responding, because this would be our reinforcer. And here is our contingent behavior. And here you see, if I give you all the reinforcers in the world, you don't behave. And as I increase the requirement, you do more and more behavior, but it begins to stop. Again, it's that asymptote. And actually, if I continued to add behavior, you would drop off the other way. So this would be our typical type of curve we'd see. All right, so take our bliss point, and we want to see, here's our constraint point. Here's our schedule constraint, and here is how much you could do to that bliss point, how much you can do on this schedule, how many minutes of recess you can get on this schedule, and so on. And so what's happening is I'm having to do more minutes of math. I'm able to do fewer amounts of recess, and I won't want to do as many. If I have to do too many math problems, I quit. But if I don't have to do any math problems, I don't engage in any, I just do recess. So too much of anything is a bad thing. All right, so why is this useful? I'll give you an example we did with dogs recently, because you know it has to be with dogs. Although I have a study with children too, if you want. We recently conducted a study with dogs to determine if human-delivered food reinforcers were equivalent to mechanically delivered food reinforcers. So here's the human giving the food reinforcer, and here is the dog giving a food reinforcer. It's a mechanical feeder. And we examined differences between dogs who had a high preference for human interaction and a low preference. And we predicted that dogs with a low preference for human contact would show a shallower bliss point function for human contact. But the feeder function should be the same for both groups because they should have an equivalent feeder function. All right, so we had 15 dogs, 8 males, 8 females. They were divided into 2 groups, 7 dogs, those were the shelter dogs. They were spayed or neutered. They had a 5-minute baseline of food rewards delivered by a human or delivered by a mechanical feeder. Here's Blair. Look at your mechanical feeder. And the dogs are classified based upon that baseline as being either a high human preference, so they had more approaches to the human than they did to the feeder, or low human preference, so they had about as many to the feeder as they did human. And our low human preference, they had 18 approaches in 5 minutes. Our high human preference group had 45. So there's a clear difference between the 2 groups. All right? So we did a median split to determine them because we couldn't ask them beforehand, do you prefer humans or not? We had to use our baseline data to test them. And again, that's baseline data. Then we imposed a contingency. We had the human sitting in a chair, and we also did this with the feeder. The feeder plays at the same place that the human would have been sitting. And all the dog had to do was walk up to the human and either look at the human or somehow touch the human, and they got a treat, or they simply had to approach the feeder and stare at it, or touch the feeder, and they got a treat. Easy peasy, right? And we had no reinforcement, that's extinction. 25% of approaches were reinforced, 50%, 75%, 100, and 200%. So they got double for each approach. They got, each time they approached, they got a reinforcer, or they got 2 reinforcers. 3 out of 4 times they approached, they got a reinforcer. Half the time they approached, 1 out of 4 times, and then never. And the dependent variable is the number of approaches they had in a 5-minute period. All right? So how many approaches did they make to the feeder? What we found was that overall, they did more approaches to the human than they did the feeder. This is both groups combined. Or actually, we have our, here are human feeders. Here's our high human preference and our low human preference. Here is the bliss point for the human, high human. Here's the bliss point for the low human. Are they different? You betcha, they're different. They both follow their bliss point somewhat. Right? Again, it's always noisy in data, but they certainly don't look alike. Here's the dogs that liked humans. Here's the dogs that didn't like humans. And here's their feeder data. The number of approaches they made to a feeder. Their bliss points were nearly identical, and their behavior to the feeder was nearly identical. It wasn't identical to the human at all. See how it's very different? But look at the bliss points. Here's the bliss point for the feeder dogs, non-human dogs. Here's the bliss point for the human preferring dogs. Very different characteristics. So simply knowing this, I'd expect that you'd have many more approaches for the human dogs, human preferring dogs, and that at some point, even though they preferred humans, it was starting to get too much. And by God, they were dipping below their bliss point at 200. These guys never really did get much below that because they weren't approaching very often anyway. We can look at the low human preference group. No difference between their human approaches and their feeder approaches. Here's our high human preference group. Here are their feeder approach or human approaches. Here are their feeder approaches. Are they different? But again, they're still falling off for the feeder, but they're not the same at all as they are for the human approaches. They really like approaching humans, even when they had the opportunity to approach a feeder. And these guys, it was about the same. No difference versus a very strong difference. But again, look, the bliss point for the non-human preferring dogs was the same as their feeder. The bliss point for the human preferring was much higher for humans, much lower for the feeder. And again, we see some distinct differences and we can make assessments. Now, there certainly are some issues with the disequilibrium model. It's not completely accurate. How do I measure baseline? Why did I use 5 minutes? Well, because it was convenient for me. Was that a good enough baseline or not? There's more research really looking into this, and certainly baseline can still be time consuming. The other thing is it only takes into account two behaviors. In my case, it was taking the food or not. But maybe sitting over there and licking yourself was more reinforcing than the food. Well, it didn't take that into account. It only took into account two behaviors, the instrumental and the contingent. And that can be problematic because we know that the behavior is much more complicated than two behaviors. And again, there's always a question of time frames. When does that reinforcer become punishing? How much of it does it take? And in this case, it looked like 200%. Well, would 300% be even more or not? We don't know. We'd have to continue out. And then where is it between 100% and 200% that we get this effect? Where is it between 25% and 0%? We got a huge increase here. How much of an increase do I need? Maybe I only need to increase so that I'm reinforcing 12.5%. I'd need more research to examine where this is. And again, we can assume that this is true for human preferring and non-preferring dogs, but I can't necessarily say that this is the same percentage for everything. Although interestingly, our data on several species now that this has been conducted with, it looks like 25 to 50% of interruptions, or that's how often we should reinforce initiations. 25 to 50% seems to be kind of magic. I get much over 75%, and I begin to see some satiation effects in most animals. So again, we haven't demonstrated that clearly, and we need to come up with some models that can explain that more accurately. But in conclusion, it's critical to predict reinforcer effects ahead of time. It's kind of silly to know it's a reinforcer after I used it. So we need to have that accuracy. Reinforcement and punishment effects depend upon the extent to which the contingency schedule constrains the free disruption of responding. We know that. How much of a disruption did my contingency impose? We know the context of reinforcement and punishment is critical, and the context may be very important. Things like human preferring versus dogs that don't prefer humans. They had very different data, so the context of the type of dog it was made a difference. And hopefully brief baselines allow me to assess that. And we argue that by returning to basic research, it really helps guide applied research and the use of these tools in applied settings. The lab drives applied research. Applied research tells the lab what questions to ask. And I think that that is a very important interplay that we need to recognize as scientists. So again, there's a strong need to predict reinforcers ahead of time. We gotta do this, guys. Otherwise, it's just silly. Reinforcers and punishers aren't necessarily things. There's no magic wand of a reinforcer or punisher. I sure wish there was. I could just have a magic wand and everything works. Doesn't work that way. But reinforcement and punishment effects depend upon the extent to which the contingency schedule constrains the free distribution of responding. And that we do seem to know. How much does it direct the behavior, and does it direct it towards a reinforcer and increase behavior, or does it direct it away from the contingency and as a punishing behavior? Got that? We're going to discuss all this and some applications of it later on. So I will stop my sharing, I hope. And I will go back to the camera. And I will tell you that that is what we're going to do today. And I hope that has been somewhat reinforcing. If not, I guess it's punishing. It's kind of two things. But hopefully it didn't push you over your satiation point and you're still hanging in there. And I will see you all on Thursday.